welcome to this lecture. Now, in previous lecture we have seen the amplifier design with conjugate matching. We could not see an example that how the input and output matching networks are designed. So, an example we will see that. So, see this problem. This is a problem from Pozar's book, again one of our reference. In my edition it is at page 573. A transistor at 4 gigahertz, its S parameters are given. Please remember that S parameter is a frequency dependent quantity. So, manufacturers specify at various frequencies the S parameters. So, at 4 gigahertz we are testing it, at other frequencies it will also change. Also S parameters are bias dependent quantity. So, if we change the DC biases, the S parameter values will also change. So, this is the problem, S parameter is given. Now, you design for conjugate matching. Now, first obviously we need to confirm whether it is stable or not. So, we enforce Rolle's stability criteria and find out that k is greater than 1, also delta is less than 1. So, transistor is unconditionally stable, also it passes the mu test that it should be. So, conjugate match design possible. We know conjugate match means gamma s is equal to gamma n star and gamma l is equal to gamma l star. We will have to do this simultaneously and then we will get the gain obtained is maximum. These are the gamma l, gamma out, gamma in, gamma s that we have discussed. Also the corresponding power criteria we have seen. So, we see the design S1, again we are writing the actual values of S1, delta turns out to be these. Now, as we have seen in the previous case that we will have to find out the gamma L and gamma S, these their solutions. So, with B1 gamma S values, so we will need to calculate B1 C1 for finding gamma S and B2 C2 for finding gamma S, and also since Rolle's test is passed. So, we know that this will be satisfied. So, gamma S and gamma L they can be obtained. So, you see we are doing that. Now, see in the presentation that B1 will turn out to be this, B2 is this, C1 is this, C2 is this. Remember B's are real values, C's are complex quantities. So, we can find the, here we are calling gamma L with a maximum because we are doing conjugate matching. So, gamma L will be this 0.87 angle 61 degree and gamma S with a maximum because it is conjugate match, that is why we are giving a subscript m. So, we have got these values and from that we can easily find out what is GTM, that means the maximum possible transducer gain that this device will give. So, you see first part, that means input part, proper choice of gamma S, that gives us a gain of 4 roughly. Then S21 part, that means the transistor gives us a gain of, device itself alone gives us a gain of 6.7 roughly 7 and this one 1.6. So, you see that if we did not do conjugate matching, we did simple matching, we could not have extracted these two parts. So, roughly 4.1 into 1.6 or in dB scale you see this is converted to dB. So, 6 dB and 2 dB, 8 dB and RF microwave designer can extract additionally for the gain from the actual device whose gain is only 8.3 dB. So, these are again. So, what is the gamma in value, you see this, and gamma out is this. Now, let us do the input matching, that we need to do input matching because we have got gamma S values. So, you see that where is the gamma S, or see the previous one, gamma S is 0.87 angle 123. So, in the Smith chart let us plot this gamma s 0.87. So, it is inside, you see this point, and 123 roughly this. This is corresponding to ZS in previous figure. ZS is impedance seen from the transistor by looking towards input matching section. That means, actually if I have this transistor here, so from here I am looking ZS, I need the input matching network to transfer this to Z naught. So, my job is from ZS I will have to go to Z naught, which is the center of the Smith chart. So, matching section is transforming ZS to source impedance Z naught. How we do it? You know, there are various ways, but we will follow the, we will make a, after this section our basically input matching network will be like this, that I have this, then I will put a transmission line, and then I will put a stub here, either shunt or short series stub, that we will see various choices. These are not unique, but we will follow a particular design. Already in the impedance matching section we have seen how to design any such things. So, what we will do, we have found ZS, tau s means that this also point, now consider this as ZS. Now, since you convert that to Ys, this is the Ys point. Now, move towards source clockwise till you hit this 1 plus JB admittance circle, you are hitting it here. So, from here, so you know that how much length of line is required, because this is the same transmission line. So, you require this transmission line, and then the length you can find from here. So, this gives line length to be 0.12 lambda, you know here are those lambda scales. So, from here you find from here to here up to this point I have 0.12 lambda, and then here you find out that what is the susceptance. This is 1 plus JB circle. So, there is some susceptance, that susceptance, since it is admittance scale, this upper portion is minus j. So, that is minus j 3.5, that you need to adjust by putting a stub. That we will do, here we have taken an open stub. So, for open means in the admittance scale, this is my open circuit. So, I need to go how much, you see this is my minus j 3.5. So, this if I take, it is 0.206 lambda. So, length is 0.206 lambda. So, from there now we do the output matching network. You plot ZL, it is here, again convert it to YL, then move towards load. Since I am moving towards load, it is anticlockwise. So, move here, you are hitting here, susceptance again here is minus j 3.5 is contributed by an open stub of length this. So, this is the final design. You see in the source side I have assumed all the transmission line and stub, their impedance level is 50 ohm, same as our characteristic impedance of the transistor. So, I have 0.12 lambda line length, and then a stub 50 ohm stub. Similarly, here a transmission line of length 0.2006 lambda, and the stub is also 206 lambda. So, now from this side the source will see a 50 ohm impedance. Similarly, from this side the load will see a 50 ohm impedance. This is the conjugately matched amplifier. Okay. So, this with this example we conclude the conjugate matching. Then we do that, always we do not do conjugate matching, because conjugate matching is a, you see that conjugate matching, because all these things are frequency dependent. So, conjugate matching is possible for a particular frequency. So, amplifier, that means with conjugate matching design I can achieve the maximum possible gain. You have seen that I can extract 8 dB extra gain etcetera in this case, but that is over a narrow band of frequency. So, the whole amplifier design is narrow band. Sometimes we do not need narrow band, also sometimes that much gain may not be needed. So, it is better to have a procedure for specified gain. So, design for specified gain. So, let us have a procedure for this. So, again here we generally now we are becoming more practical, and we have seen how to do bilateral design. Here we make an unilateral approximation, that generally all practical transistors that we will be using unilateral. If you cannot make this unilateral assumption, you know how to design here, that you can do. So, when we design for specified gain which is less than the maximum gain possible, maximum transducer gain possible, definitely we are deliberately putting some mismatch in the device. We are not properly conjugate matching, we are putting that mismatch, and that is why we are getting less gain, but we are satisfied with that, because that much mismatched, that much power loss etc. we can suffer sometimes. If not, then do the conjugate matching, which is the best design. So, unilateral case, actually you see, if I make unilateral thing, actually my GT in unilateral, let us call that GTU. So, actual device, if it is not unilateral, can I say that I am committing an error of the order GT by GTU. So, GT is my actual thing, GTU is my actual thing. People have shown that this has an bound, that both lower bound and upper bound, that can be expressed by a parameter u. It is a unilateral case figure of merit. So, this error or this ratio GT by GTU, that means if I make this assumption, I am committing an error or off the my gain is off the mark by this, that is have an upper bound and lower bound, where u is given by, it depends on all S parameters of the device. So, this name of this parameter u is called unilateral figure of merit, and people have shown that usually this error, it is within 0.1 to at the most 0.34 dB. So, I am not suffering in this. If I make an unilateral approximation, then my error that I commit in getting the gain, that is not much. So, that generally can be done, but that simplifies the procedure. So, let us see that procedure for specified gain. So, specified gain. So, that means people will now tell me that you get this much gain. Now, as I already said that I have the whole gain, that always in the GTU case also I can divide as GS, U, G naught and GLU. So, input matching section, output matching section. Now, henceforward I leave this subscript U. So, I can say that what is GS? We know under unilateral thing it is simplified, the gamma L does not come into picture, and it is simply 1 minus S11 tau S whole square. So, you see that GS I can choose just from gamma S, or gamma S I can choose by knowing what is my GS requirement, that means input matching circuit, how much I want to have. Similarly, GL can be written as 1 minus gamma L square by 1 minus S22 gamma L square. The moment I have this, you see that output side I can design from the specification of GL. So, I have overall specification of this, I know this value, this is S21 square of the transistor. Now, this 2 is in my hand, I can have any choice input matching and output matching, some gain, some portion I take from here, some portion I take from here, and I do that dB gain. So, in the dB scale, you know, this is nothing but I can write it as GTU in dB is GS, or let me under all are under this approximation, GS dB plus G naught plus GL dB. So, there you can see that I can choose that, okay, suppose it is 11 dB required, suppose this is 8 dB. So, 3 dB, now it is up to me to distribute, either I take 2 dB here, 1 dB here, or 1 dB here, 2 dB here. So, this now out of this you see this GS value, GS is maximum if I can choose gamma S is equal to S11 star. Also this GL will be maximum if I can make gamma L is equal to S22 star. If I can do that, then immediately there will be maximum this thing, just from here you can see, and I can write that value, that what is GSM, that will be a GSM, that is 1 by 1 minus S11 square. So, maximum I can do depends on the S11 parameter. Similarly, from the output matching section, GLM I can say this is 1 by 1 minus S22 square. So, now what you do to facilitate the design, we define a normalized gain function, normalized gain function. So, I have two such gain functions, GS, small gs and small gl. What is GS? GS, which is my specified by the maximum that I can get. Similarly, what is GL? It is GL by GLM. And what is this? If I write the expression, all the expressions are there, you simply write it 1 minus tau s square by 1 minus S11 tau s. This is my GS, and maximum is 1 minus S11 square. This was denominator, so it has gone here. Similarly, here I can write 1 minus gamma L square by 1 minus S22 gamma L square 1 minus S22 square. Very elegant, and it is obvious that 0, this is the benefit of normalization, that these normalized gain functions are lying between 0 and 1. Now, you see this one I can just manipulate, as I have done in case of the conjugate matching. What we did, we have written GS as a function of GL and GL as a function of GS, and then two equations, two unknown, we did that. But here already input and output are uncoupled. So, from one equation, suppose from this equation I can find out what is the solution for gamma s. From this equation I can find out what is solution for gamma L. I can choose accordingly. So, we will do that we will write this GS equation. Now, forget this, GS is this, from there we will find out the solution for gamma s. One equation, one unknown, I can always do that. So, GS I write as 1 minus, again I am writing 1 minus gamma square by 1 minus S11 gamma s square into 1 minus S11 square. So, solve for gamma s. If I do that, again I get something like this. So, you see again this is a complex number, this is a complex number, this is a real number. Gs, small gs is a real number. Now, what is this? In the Smith chart, if you plot this or this locus, can I say this is same as before? This is an equation of a or locus of a, this locus will be a circle with this is center, this is the radius. So, we call that. Now, what is this? This Gs is a specified value or a constant value. So, we call this as constant gain input circle, because here we are choosing the input side. So, constant gain input circle or constant gain circle for input section. So, what will be my Cs? Cs will be Gs S11 star by 1 minus Gs S11 square, and what will be my radius? Radius will be root over 1 minus Gs 1 minus S11 square by 1 minus Gs S11 square. Gs is specified, S11 value I know from the S parameter. So, I can find out this and I can plot that on the Smith chart, that will be a circle. Similarly, I can do for the other thing, that constant gain output circle. So, here we have solved for Gs, there will be from this normalized gain function, you solve for gamma L, that locus is again a circle, and there the Cl, the center will be Gl S22 star by 1 minus Gl S22 square, and radius is root over 1 minus Gl 1 minus S22 square divided by 1 minus Gl S22 square. You see, so from this we will see an example that how to choose, but here let us see these two, that this constant gain input circle and constant gain output circle, there are some points that needs to be underscored, that we can see that for various values of gains, given gains, I can have various because as I said that suppose I decide input side, I am not sure whether to take 1 dB or 2 dB or 0 dB or minus 1 dB, which gain I will take. So, what I will, but one thing is true, that centers of each family of circles lie along a straight line joining center of Smith chart to either S11 star or S22 star, whatever the or S22 star. You see, the center is, this is all some real number. So, Cs is along S11 star, in the Smith chart that is a complex number. So, it is along S11 star, or Cl is along S22 star. Then another point is when Gs is equal to 1 or Gl is equal to 1, what happens? You see, if CS GS is equal to 1, then this becomes simply CS becomes S11 star, and this center becomes S22 star. So, then the center simply is S11 star or S22 star, as the case may be. Also, it can be shown that 0 dB gain circles pass through center of Smith chart. So, from here you can always draw the circles plotted on Smith chart, and then you can choose which gamma s and gamma l value, so that you get the desired gain. Now, this choice is not unique, there is no unique design, this is your A, but one thing you try to choose gamma s and gamma l as near to the Smith chart center as possible, because that will reduce mismatch. Though you are deliberately giving some mismatch, so you cannot choose the center value, but if you choose it keeping your gain requirement, if you choose it as near to center as possible, that will be better. Amplifier design for specified gain. So, here you see unilateral case, these are all these things. So, again unilateral figure of merit. So, Pozar's problem, page 625, design an amplifier to have a gain of 11 dB at 4 gigahertz. The transistor is given with this. The first check the unconditional stability, S11 is less than 1, S22 less than 1, you see it is unilateral, already S12 is 0. So, maximum value will be obtained here. So, find out those values, and you see the I have written everything. So, GTU, so G from the input section here, instead of S I am calling G1. So, input section can give you maximum 3.6 dB, the output section can give you maximum 1.94 dB, and the transistor itself gives you a gain of 8 dB. So, maximum you can have 3.6 plus 8 plus 13.5 dB, but it is required 11. So, you can cut down here or here as per your thing. So, you draw constant gain circles, determine. So, let us say that we have determined here, suppose this is the 3 dB circle in the input side, this is the red one is 3 dB circle, the green one blue one is 2 dB circle. Now, where I will choose, you see that a prudent choice will be as near to as possible. So, if I decide I will take 2 dB from the input side, I will choose the point here, that is a good choice. I can choose also here, but if I choose it here, that will be more prudent. So, here you see that gain is this, normalized gain factor you see, distance of circle, radius of circle. So, by that we have plotted constant gain circle. So, for 3 dB circle these are the values given, similarly for 2 dB these are the values given. Similarly, for the output side you see we have chosen these two, that for 2 dB circle like this, then choosing we have decided that already 8 dB the device was giving, 3 dB we have decided from the input we will take 2 dB and output we will take 1 dB. So, choose this, you see I have chosen the nearest point for this. So, that gives the value, if I read this value it is 0.32 120 degree, and for the load I have chosen 0.22 70 degree. Now, gain you can find this, and you can design the matching networks, because the moment you choose gamma s is this, you can find out, locate that point gamma s, then convert to y s, then see where you are cutting the 1 plus j bit circle, from there you can design the step. So, here we have seen that 0.18 C, 0.18 lambda, you will have to have a transmission line, then you will have to cancel this stub. So, that similarly gamma s. So, here I have given all the values, and by that again you can do the input matching and output matching. So, this is the final circuit. You see I have used a transmission line, then a stub of this much length, then here also a transmission line and stub this length. So, this constant gain thing that gives you 50 ohm here, 50 ohm here, though actually the source and load impedances were different, but with matching now it appears as 50 ohm here, 50 ohm here. So, this is the total design for given 11 dB thing. I hope now you understand how to design for constant gain circle. Two more things we need to see, that one is that sometimes we need to have, instead of gain, another very important parameter sometimes, particularly for LNAs, that is the noise figure. So, we will have to make a particular noise figure or minimize the noise figure. Gain may be anything moderate gain. So, that design we will see. Also we will see broadband design, also we will see that sometimes in a power amplifier the non-linearity things comes. Stability we are enforcing everywhere in every amplifier, but if I give very high input then non-linearity comes. So, how to design under that non-linearity or to keep that non-linearity away, how to design amplifier, because if my amplifier has non-linearity then sometimes I may give rise to some additional spurious frequencies which is not desirable. So, how to make power amplifier design. If we do that, this whole RF amplifier design part will be completed. Thank you.